Okay, thanks, Jonah. What I'm going to do today is tell you how we get the data, where the data comes from, and then the other experts in the room will actually tell you what we do with the data and what you can do with the data. So first, I also want to add my welcome. This is quite an exciting time for us. And you're going to get a hands-on experience working with LIGO data with the software tools. You'll be in the hands of experts, which means at the end of this, we hope that you'll become experts. And I looked at the participation list, the attendee list, and you come from a lot of backgrounds, actually. I think there are high school students here, there are undergraduates, graduate students, professors, people from who are astrophysicists, but also people who aren't. So it's a broad spectrum, and that's great. I want to emphasize that all of the people who will be teaching you are really experts. I've known most of them for long periods of times, and these people are truly the experts in understanding LIGO data and analyzing it. So you're really in good hands. So again, I think this is going to be a great experience for you. So what I'm going to talk about, four things, maybe three things, because I'm not sure I'm going to have time to get to the last one. So my job is to explain to you how the detector works. All right, I'll start with sort of what are gravitational waves and why they're interesting. Then I'll get into the interferometry, the way we detect these gravitational waves. And then I'll go into what I call advanced interferometry, what advanced LIGO is. And then I'll talk a little bit more about what happens even beyond LIGO. So we have a global network of detectors. And in fact, you'll soon be able to access data from a detector in Italy called Virgo. So I'll give you sort of the where we're going with that. Okay, so what are gravitational waves? Well, I suspect many of you in here know that already, but just let me give you a sort of a brief primer. They come out of general relativity. They are propagating solutions to the Einstein field equations, which describe gravity. And they have very unique characteristics. They travel at the speed of light. They have two polarizations, and they carry information about bulk mass motion. So unlike electromagnetic waves, which basically are produced as charges move, gravitational waves are produced as masses move and accelerate. And so that equation there in the upper right-hand side is basically how you calculate the strain of a gravitational wave. And what do I mean by strain? What interferometers measure, what we measure in our detectors, is a change in length per unit length. So as a gravitational wave passes over you, that nice H, that one on the left-hand side there, what it's doing is it's stretching space in one dimension, compressing it in the other dimension, and then this just sort of keeps oscillating. And so in this case, the gravitational waves would be coming from you. Now the problem is this, that these strains are mighty tiny. All right, a strain from two 10 solar mass black holes colliding with one another. And these things are moving at relativistic speeds, about half the speed of light. They're orbiting around one another at 300 or 400 hertz. In this case, I've put them about 500 megaparsecs away. They produce a strain that's 10 to the minus 21. Okay, so what we're trying to measure, all right, is 1 part in 10 to the minus 21. That's like trying to measure the distance from here to the nearest star, Proxima Centauri, to about the width of a human hair. All right, so that's the scale at which we are making these measurements. All right, now, interestingly, Einstein himself didn't believe there was any interesting physics to be learned from gravitational waves because of the problem with measuring something so tiny, and it took 100 years from the time he predicted them to the time we detected them. But there's actually a lot of things we can do, and I'm not going to go into too much detail in this, but there are basically a number of different classes of gravitational wave sources. So there are the sources that we know exist because we've detected them, the compact binary system, so two compact objects like black holes or neutron stars, or maybe a neutron star and a black hole, orbiting around one another, excuse me, colliding together. These are sources that are nice because we know how to model the waveforms, and that actually helps a lot with how we search for these sources. There are transient sources, say gravitational waves produced in supernova explosions. They're tough because we don't really know how to model them. There are sources from, there are stochastic noise sources, so these would be noisy backgrounds. They come from either the Big Bang themselves or more likely the kinds that LIGO will see will be a superposition of all of the black hole mergers and neutron star mergers that have taken place in the past. Those remnants are still with us because gravitational waves never get absorbed. They don't interact with matter, which is why they're so hard to detect. And then finally, continuous sources like spinning pulsars. So if you have a pulsar or a neutron star that may have a crustal defect, it produces a very monotonic signal. And that's the thing. Each of these kinds of sources produce different characteristic signals. Some are transient, some are continuous. The ones on the top are transient, the ones on the bottom are continuous. Some are modeled, and some are not modeled. Okay, so that is a very brief introduction into gravitational waves and the astrophysics of gravitational waves. So what is LIGO, and how do we detect something of that size? So LIGO stands for the Gravitational Laser Interferometer Gravitational Wave Observatory. The LIGO detectors were built and are operated by Caltech and MIT with help from some other institutions. LIGO science is conducted by the LIGO Scientific Collaboration, and after this workshop, hopefully you all. I am at Caltech. I lead the LIGO laboratory, which is about 180 staff, including the two observatories, one in Livingston, Louisiana, one in Hanford, Washington. That's where the observatories are. And then there's a much broader group of people, and in fact, I think everybody who you'll be hearing from today are members of this broader LIGO Scientific Collaboration. It's quite a big group of people. All right, so what's an interferometer? Well, let's start with the gravitational wave. So this is the gravitational wave coming at you, and it's stretching you and squeezing you, but as you now know that you can't really see it because it's so tiny. Well, it turns out that gravitational wave detectors, interferometers in particular, are sort of uniquely positioned to be able to detect a gravitational wave, because what's actually stretching and compressing here is literally the distance between any 2 points. So if you were to put a ruler down on the x or y axis, the ruler would be stretching and compressing. Well, that's what an interferometer measures. So an interferometer is a laser, all right, it's a beam splitter, that's that thing in the center, and it splits the laser light into two equal proportion beams, equal powers, and then as it goes up and bounces off two mirrors, and as the gravitational wave goes by, what happens is the distance along the y coordinate, let me see, okay, so let's call this the y arm, let's call this the x arm. This distance gets longer, this distance gets shorter, and that changes the interference pattern here. So you can think of a gravitational wave detector, an interferometer, as a transducer of gravitational waves. And I'm going to do a little bit better, give you a little bit better sense of how this works. All right, so again, here's the laser. And now I'm going to color code the wavelengths. And the beautiful thing about laser light is that it's coherent, and those wavelengths have very, very well-defined lengths. So they're rulers. In fact, they're the universe's best rulers. So they come back, they combine. In this case, they're destructively interfering. So right now, there's no gravitational wave passing over this interferometer. But what will happen is a gravitational wave will start to pass. It will start to change the distance, relative distance between the x and y arms. And you can see that now the interference pattern changes. It's a dynamic interference pattern. And that screen there is actually a little photodiode. So what it does is it records the signal. So what a gravitational wave interferometer does is it's a transducer. It's a receiver. It basically takes stretching space-time and turns it into interfering light, which is recorded by a photodetector. So what you've got is basically you can record gravitational waves. Okay, now, all right, the problem is that these wavelengths in the example that I used are about 1 micron, so 10 to the minus 6 meters. And here, when I did the little video, it looked like we were sloshing back and forth by about a micron. In fact, we're not. We're slashing back and forth by a tiny, tiny fraction, about a trillionth of a micron. And so the question is, how do you do that? How do you accomplish such sensitive measurements? How do you measure something that's 10 to the minus 21? All right. The first thing I should tell you, actually, let me go back here, is LIGO takes advantage of two things. When you're measuring a strain, you're trying to measure a displacement, that's the delta L in the numerator, and then over a baseline, and that's the length in the denominator. In our case, the lengths are 4 kilometers. All right, so it's about 2.5 miles. So in that case, what we have to measure is about 10 to the minus 18 or 10 to the minus 19 meters. So that's the displacement that we actually have to measure. That's the physical change in distance between the x and y arms. All right, so how do you do it? Turns out, use light. All right, light is a wonderful thing. It comes in discrete units. When you think of light, you think it's continuous, but no. Quantum mechanics tells us that it comes in discrete units, and these units are called photons. I think everybody's probably familiar with that term. And when you discretize something, when you quantize something, you naturally introduce uncertainty. This is what quantum mechanics tells us. So photons obey the Heisenberg uncertainty principle, which means that if I have a beam of laser light coming at me, I can't accurately say if a photon comes in and hits the detector, I can't accurately say when the next photon is going to come in. I can probabilistically say when it's going to come in, but it obeys basically a statistical, there's a statistical variability. It's basically Poissonian statistics. And so the uncertainty, all right, in the number of photons arriving at the detector at a given time over the number of photons goes as 1 over the square root of the number of photons. All right, so basically, if a gravitational wave passes by by the interferometer, all right, it's going to produce a change in the interference pattern due to the fact that the photons are arriving at different times. All right, some photons are arriving when you're on a constructive interference. There's less arriving when you're on a destructive interference. But because of the fluctuations, all right, of the photon field, there's sort of a minimum sensitivity that you can achieve where you can't distinguish whether the photon fluctuations are actually from the gravitational field itself or from the passing gravitational wave, or from just the natural fluctuations of the photon in the laser field. And you could do a simple calculation, maybe 10 lines or so, and you could show that the limit at which you can detect a gravitational wave, so this is what we call the shot noise limit, because this uncertainty principle in laser physics is called shot noise, is 1 over the length of the interferometer, and then there's a square root here. H bar is our famous Planck's constant, c is the speed of light, lambda is the laser wavelength, 2 pi, of course you know, and p is the power. So that's related to the number of photons here. And if you just put in some numbers, all right, in our case we use, and these numbers are somewhat made up, somewhat not. This is the laser we use. 100 watts seems like a good number, and 10 kilometers, a little bit longer than LIGO, but it just gives you a sense. You do this calculation, you get 10 to the minus 23 in per root hertz. So that's another thing that we measure, basically amplitude spectral densities. All right, but the important thing here is that you can see that this number is on the order of 10 to the minus 21, maybe even a little bit less. So just by using the right laser with the right amount of power and a long interferometer, we can get to this 10 to the minus 21 or better that we're trying to get to. Okay, so the challenge with interferometry is noise. All right, if you build an interferometer on the Earth, you are subjected to a number of natural phenomena that are going to perturb the interferometer. So again, anything that changes the distance or apparently changes the distance between this point and that point relative to this point and that point is going to manifest itself as a gravitational wave. And so your job as the maker of an interferometer is to minimize all the ways that can happen. So how do we do that? All right, or what are we up against? Well, first we're up against residual gas scattering. So the atmosphere, it turns out, changes the arrival time. It delays photons, as that's what the index of refraction is. And so you've got to get around that. And the way we get around that is using big vacuums. And I'll say a little bit more about that later. Lasers. Actually, my background before I got into gravitational waves was in lasers. And lasers, everybody thinks are perfect. They're the most beautiful light sources in the world. In fact, they're very imperfect. Any laser has laser wavelength fluctuations, so the wavelengths change as a function of time. So sometimes it's 1.064 microns, sometimes it's 1.0640002 microns, and that happens dynamically. All right, so there's just inherent noise in the production of laser light, and the amplitude, the power fluctuates, and of course based on what I said before, you should immediately think to yourself that that's also something that could lead to a spurious signal. All right. A big one and a tough one for us, and one that we spend an immense amount of time, energy, money, and engineering on, is seismic noise. The Earth vibrates, and it vibrates pretty wildly. Right now, the Earth is actually moving below your feet with about a 1 micron amplitude at low frequency, a little bit less than a hertz. All right, and so our mirrors have to be capable of being still in the band that we want to measure gravitational waves to about 10 to the minus 18 or 10 to the minus 19 meters. So there's a factor of 1 trillion or even 10 trillion difference there. So we've got to basically isolate the mirrors from the Earth's motion, and that takes a lot of technologies that I'll show you later. The mirrors themselves actually cause problems. So everything is at a finite temperature, and anything that has a finite temperature, physics tells you, has energy in it, right? And energy causes motion. So in fact, these mirrors, the surface of these mirrors are moving, and they're moving very tinily, but comparable or just a little bit less than the gravitational waves we're trying to detect. And in fact, thermal noise is one of the noise sources that limits us, as you'll see later in the talk. All right. Now, you might say the way around that is to lower the temperature of the mirrors, and you'd be right, and that's something that we're looking at, but we haven't done it yet. Finally, there are two kinds of noises. One I've already explained. It's this quantity called shot noise due to the random arrival times of photons. But the other is interesting. Photons have momentum. They have energy. They have momentum. And so if you have photons randomly arriving on the mirror, all right, and there's a lot of photons, the powers in these interferometers are quite large, they actually push the mirrors around. They push the mirrors back and forth, and that kicks the mirrors. So that's a displacement noise. All right, and so it turns out that these are sort of opposite sides of the same coin called quantum noise, and depending on what frequency band you're interested in, as I'll show you later, will determine whether you want to deal with radiation pressure or shot noise. So, all right. So that's the basic idea. The basic idea is to build a big interferometer, all right, put it in a big vacuum, make really good lasers, and pump it out so that it's there's no atmosphere there, and start looking for gravitational waves. And the gravitational waves then are produced right there. All right. Now, so that's introduction to interferometry. Let's now go into the advanced case. Maybe I'll stop there. Does anybody have any questions? Yeah.
About the noise dimension, I would like to ask whether some of the noise are color noise.
Are what?
Color noise, not the typical white noise. So can we expect a feature of this noise?
Yeah. So the shot noise is white, but we do something to the interferometer itself. Actually, puts some color in the noise. So it's actually not white. It rolls off as 1 over as f. As f increases, it starts going up as f at higher frequencies. The rest of the noises are not white at all. You'll see that actually later on when I get into it. So that's advanced interferometry. Anything else? Yeah.
If seismic noise is such a huge problem,
Why not go into space?
why is there a detector in Washington, which is like right next to the fault lines and stuff?
Yeah. Good question. Turns out there's a lot of other reasons you would put a detector. There are lots of requirements for where you site gravitational wave detectors, and no place is perfect, all right, on the Earth. And so consequently, Washington was actually pretty good. There was a quake I think in Seattle in 2001 or something like that did a little bit of damage to us. But we now know how to ride out quakes, and we protect the mirrors in the case of a quake and things like that. So, all right. Okay, advanced interferometry. All right, so here's what LIGO looks like in a more complicated sense. So you'll recognize the basic elements of the interferometer, but now you see a lot more mirrors, and you see mirrors hanging on mirrors and mirrors hanging on blue things. So a little bit of walk through this. Here's our laser. It doesn't quite work at 125 watts yet, but eventually it will. What are all these mirrors doing here? Well, they're actually enhancing you can think of it in a number of ways. They're enhancing the power that goes into the interferometer through something called passive amplification. They're enhancing the the storage time in the interferometer, so the light actually spends a good fraction of a second inside the interferometer, and that allows it to interact with a fair fraction of the gravitational wave as it passes over. And then there are things called recycling mirrors, which actually work to recycle either the laser or the power. So let's walk through this. So here's the laser, here's the beam splitter. The first trick we play is to use Fabry-Perot arm cavity. So instead of having just one arm that's 4 kilometers long, we actually, very close to the beam splitter, put a second mirror in each of the arms. And that has the effect of actually, if you keep the cavity on resonance, in other words, if you make the distance of half a wavelength exactly between these two mirrors, what will happen is as you put laser light in, the light gets stored and it gets amplified up. And when you do all the math, we take this 125 watts and turn it into 700 kilowatts. All right. That has the effect of the way I like to think of it is it acts as some phase gain. So as a given gravitational wave passes, when it changes the arm lengths between the X and the Y arm, the phase shift that you get, the light, the phase shift that the light experiences when it comes back to the beam splitter is amplified by something called the finesse, or almost the number of round trips of this cavity. So that's the first trick, and that actually gives us a good deal of bang for our buck. Second trick we play is the fact that the light, when we configure the interferometer such that when there's no gravitational wave, all the light comes back this way, and that's wasted. What's important in terms of shot noise is the amount of power that gets to the beam splitter. And so what we do is we use another sort of pseudo Fabry-Perot cavity. The light's very coherent, so it has a well-defined phase, comes back, and then we just inject it back into the interferometer. So that basically allows the light to be stored even more. And in this case, the gain of this cavity, if you will, is about 35 or so. And then we have another mirror over here, a signal recycling mirror, which allows us to actually, if we want, we don't use it, but we can tune the responsivity of this. But this allows us actually to extract the gravitational wave at the time when it's most sensitive for us. And then at the end of this is a photodiode. And the H of t, so the data that comes out is a time series, digitized at 16 kilohertz. For the LOSC, the data that you're playing with actually is further down sampled, I think, to 4 kilohertz. Although at some point we're going to actually release 16 kilohertz data. So, all right. So let's walk through this. All right. So this is a more sophisticated version of what I just showed you before. These are the noises that compromise the interferometer, and they come in two flavors: displacement, in other words, noises that shake the mirrors, and sensing noises, noise that change the flight time of the photon relative to its normal vacuum flight time. All right. And these curves here, this is going to take some explanation, so let me walk through it. So this is frequency. All right. This is 10 hertz. This is a kilohertz. And this is basically the bandwidth. This is the bandwidth with our detector works. So we would call this a relatively broadband detector, in the sense that it can detect gravitational waves over at least 2 and a little bit more orders of magnitude in frequency, but it's limited. Below 10 hertz, the responsivity falls off, and above a kilohertz, there's this is the noise question that was asked. So this is the noise spectrum of our instrument by design. All right, this is not what we've actually accomplished yet. And then all of these other guys right here are different sources of either displacement or time of flight noise. And you can either model them, and in many cases you can actually measure them. All right, but you're limited by 3 of them. 2 of them are quantum noise at low frequency. This is radiation pressure. At high frequency, this is photon arrival time fluctuations, or shot noise. And in the mid-band, here we're limited by the fluctuations of the mirror surfaces themselves, actually due to the optical coatings that we put on the mirrors. So the name of the game in interferometry is to understand all these things, model them, and that tells you how to design your interferometer. And then you've got to worry about what I call technical noises, and there are hundreds of these. I mean, there's so many technical noises in LIGO, it's mind-boggling. And when you put the interferometers together, you have to sort of systematically go through, measure all these things, and then try and beat them down. And in case it's not, so on the y-axis, of course, is strain. So in that units of per root hertz. So this is 10 to the minus 24. This is 10 to the minus 23. And in case it's not completely obvious to you, lower is better. All right, the name of the game is to make that curve as low as possible. All right, here's a more sophisticated picture of the interferometer showing all of the parts of the interferometer, and I'm going to walk through some of these in detail. So let me start by subsystem here. So this plot is, don't read it carefully, it will make you, unless you've had a lot of coffee, you'll start dozing off. But what I want to point out here is the complexity of this. So we design these interferometers in an engineering sense. So there are engineers who come in and who say we have to sort of figure out how to break the interferometer up into different sort of pieces that make sense from an engineering standpoint. So there's, for example, a data acquisition system. This is very important to you. All right, there's a core optics component. So this is everything having to do with the mirrors themselves. There's a vacuum system. This is basically the vacuum that thing is, the detector is housed in. Something very important, but I won't have time to talk about, the thermal compensation system. Basically, we have to be able to tune the amount of power that gets into each of the mirrors to keep the interferometer operating stably. And this is sort of the heart of it, interferometer sensing and control. Here's the laser system. The two systems that are most important in terms of getting to low noise at low frequencies are these, seismic isolation and suspensions. We now have squeezed light, but I'm not going to talk about that. Point of this whole slide is the following. If you look at the number of drawings, servo loops, control loops, and data rate, this gives you a sense of complexity. So there are almost 10,000 different drawing components here. There are about 3 million components, because we have to reproduce them many, many times. The number of servo loops, these are control loops, 353, and they're all very, very, well, many of them are very, very coupled to one another. And the data rate is 55 megabytes per second. All right, so a lot of data comes off here. And I told you that the strain data, the HFT data, is only 16 kilohertz. All that extra data is what we call ancillary data. So we monitor everything in LIGO, so we know that the interferometer is behaving properly. So let's walk through it. Here's the front-end laser. It is a work of art. It produces 200 watts, although right now it's not quite producing 200 watts. Laser physicists love to show mode plots, so it's a beautiful Gaussian mode, and it's very hard to work with because it's very sensitive to contamination, so you have to work in a clean room. Suspensions are marvelous. To me, this is really a tour de force in engineering. We basically use the idea that if you hang something on a pendulum or a spring, harmonic oscillator, if you calculate the amount of displacement, so if this is moving by big X, how much of that motion is a function of frequency, gets down to this part, little x, you can do that calculation pretty easily, and it basically falls off as 1 over the frequency squared. And so we take this concept and put it on steroids. We actually have 4 suspensions. So here's the mirror. Here's another mirror. It's actually not used as a mirror. It's just there as part of the suspensions. And then there are 2 more stages, and then these are all suspended. So we basically have 4 chains of these things. And if you calculate the transfer function, all right, so this is basically the motion at the mass here where we want to be quiet over the motion at the platform here up above. All right, it's a function of frequency. There's a resonance, and of course at the resonance the motion is amplified, but it falls off basically as f to the 8th. So very quickly you can see that you can go from motions of microns, things like that, due to seismic motion. You're down by a factor of 10 to the 10 if you go up towards 10 hertz. And again, engineering tour de force, we actually use fibers, glass fibers. So the mirrors themselves that detect these gravitational waves are hung by glass fibers. All right, the mirrors themselves are also state-of-the-art. This is a phase map of the mirror. So what you're looking at, the false color, is basically the surface deviations from a sphere, and these are measured in nanometers here. So this is one of the most perfectly figured mirrors in the world. It's also low absorbing. It has a lot of technology and material science that gets put into it to make it work, but it does work. Here's the control system, and this is basically the sort of a toy model of the control system. How you have to keep the mirrors in the right position. You have to know that they're in the right position, and then you have to keep them in the right position. And how do we do that? Well, the way we know they're in the right position is by using another laser field, shifted off by a small amount, a radio frequency amount, comes in. Here's the arm cavity, the Fabry-Perot cavity. The light that is on resonance with the cavity gets in, bounces around quite a bit. The light that isn't on resonance actually reflects off the front surface of the mirror and is used as a reference. So some of the light that reflects, that gets into the cavity and transmits back, mixes, or we say beats, with some of the light that doesn't get in, the frequency shifted light, and beats together here, and that serves as a reference, and you get something called an error signal here. So as one of these mirrors moves by a small amount relative to the other, bit nanometer, you can see that you've got a very, very steep slope here that this can sense. And so that allows you then to basically feed back. There's a low-pass filter and there's an amplifier here to push the mirror back towards the resonant condition. And we actually do this also in two ways. We can actually change the laser wavelength very rapidly on a sort of a hundreds of kilohertz time scale, or we can push the mirrors, but that's actually much, much lower. All right, so that's the concept. It's actually much more complicated than that. This is, oops, I'll go back, there we go. This is what it looks like in reality, and again, if you stare at this too long, you'll start to get cross-eyed. But basically, all of these different colors represent different laser fields that are generated in electro-optic modulators that allow us to sense all of the degrees of freedom. In other words, the differences between all lengths of all the important cavities in here. And at the end, there's something called an output mode cleaner, and that's where your signal comes out. Okay. Finally, the vacuum system, which doesn't seem like it's important, but it turns out to be really important. It consists of about almost 10,000 cubic meters, 30,000 square meters of surface area. So this is the tube. It's about 1.2 meters. It's about 4 kilometers. It's welded together, and it has a vacuum of about 1 10 billionth to 1 billionth of an atmosphere. No, it's actually better than that, 1 trillionth of an atmosphere. No, it's 1 billionth of an atmosphere, and that's at each observatory. And these things actually leak, and finding leaks in them is no easy thing to do, but we managed to do it. All right, so you put it all together, and I'm going to run out of time here, so I want to be quick about this. And here's what you actually measure. So this is the design curve that I showed you earlier, and this is what we were able to achieve. This is just showing the Livingston performance. Now, if you look at that, let's go back first. If you look at that, you'll say, well, you're not meeting your design goals yet, and you're right. And so we're still working on that because these things are exquisitely delicate and sensitive instruments. But the other thing you'll notice is that there's lots of noise in this. So there are lots of lines in here, and you might ask yourself, relative to this nice, pretty model performance, what are these lines? And the answer is that some of them, they're all known. Some of them are line frequencies. So, for example, we in the United States live in a world where 60 hertz noise, our power mains are at 60 hertz, so there's a noise at 60 hertz, and all of the higher harmonics, 120, 180, etc. There are calibration lines put in here. I think, which one? This is a calibration line. There are a few others. I think that's a calibration line up there that allow us to actually calibrate the instrument. And then some of these lines, this guy and this guy, are actually basically violin modes. The fact that we're suspending the interferometer means that those fibers are under stress, and they vibrate because they have energy in them, and that's basically the fundamental frequency and the higher harmonics that they vibrate. And then there's some other stuff going on here having to do with different degrees of freedom of the suspensions. Anyway, this is all well understood, and in fact, one of the things I think you'll hear in one of the next talks is characterizing the data and making sure that the data that comes out is clean, because there's lots of things that can corrupt the data, and that's, before you analyze the data, you have to know that you have good data. All right. Oh, yeah, just a punchline here. In this band right here, we can achieve about 3 times 10 to the minus 19 meters, so that's quite good. All right, so to briefly finish up, let me talk about the rest of the world. So in the name of the game in gravitational waves is actually doing not just gravitational wave astronomy, but doing multi-messenger astronomy. So this is looking at a binary neutron star colliding with one another And that should not only produce gravitational waves, but light in the form of all kinds of, across the electromagnetic spectrum, radio, visible, gamma rays and X-rays, possibly even neutrinos. And the idea is if you can see all this happen at the same time, you're going to get a much better picture of how gravitational wave, or how this object actually behaves. You'll be able to probe into the physics deeper. Oops, this didn't work anyway. The problem is that interferometers are not directional. They can't actually point at something, unlike telescopes. So the idea is you've got to get around that. And the way you get around that is to actually use multiple detectors. So there's a number of detectors. These are the two LIGO detectors. This is Virgo, detector in Germany called GEO, and then a couple of detectors that are under construction. That's the spectrum there. And you can see when they're operating. So these guys are all operating now. Kagro will be operating in Japan in 2019, and then we're building a detector, a clone of these two detectors in India. And that will allow us to actually have a network that's able to relatively precisely, and you'll see what I mean by that in a second, localize sources in the sky. All right, so this just is the case, the science case for why you want multiple detectors. If you want to look at a binary neutron star and you want to, and you have three detectors, Hanford, Livingston, and Virgo, these ellipses here are basically the precision with which you can localize an event on the sky. And you can see that there's some, and this is basically the sky projected onto a globe. So you can see there's some places where it's really good, there's some places where it's really not so good, and there are some places where it just doesn't work at all. And that has to do with the geometry of how gravitational waves interact with the detector. So this is a calculation, a model. All right, but if you just add one more detector to the network, you can see that this cleans up nicely. And this allows you to actually have a full sky coverage with all the detectors. So I think I'm done here. I will point out, and I think the slides are going to be available for you, that if you want more information, there are really three sources that I can point you to. The first is a book by Peter Salson, which was just released in second edition, that basically goes into much more of the physics behind interferometer gravitational wave detectors. The second is a paper describing advanced LIGO. It's a much more, it's a more complex paper and more terse, but it gives you more about how advanced LIGO works. And finally, Rana Adhikari wrote a nice review article in the Reviews of Modern Physics that talks about all this. So I'll stop there and take questions. Thank you.